So in this lecture we'll be learning data representation methods. We encounter various types of data when we're performing data mining. So we have categorical data which have discrete categories. For example, colors could be a categorical data. And numerical data where we have either integer values or, for example, real values. And the strings or string or textual data could, for example, come from documents, words in a document. And we have time series data where we have a clear chronological ordering of our data points. So there are several things that we need to consider when we want to represent our data using one of those data types. So what's the best type to represent the value of a given variable? So that depends also on whatever algorithms that you're going to use on top of this representation. And if you have situations where your data points are in different scales or ranges, then you might also have to readjust your scales to some kind of a normalized range. So let's take a concrete example and see how this sentence can be represented. So we have this sentence that says the burger I ate was an awesome burger. And there are various ways that you can represent this. You can take all the words in the sentence, or you can take just a set of words ignoring the duplicates, or you can represent it by a vector where you have the keys as the words and the values are the frequencies of those individual words. You could also represent this using letter frequencies instead of words, but that's not going to provide that much information about what was said in the original sentence. So data representation is one of the earliest things that needs to happen in the data mining application pipeline. And what we can actually mine will determine by whatever representations we are using. There is no single best data representation method, and if you use the kind of wrong representation, then you might end up getting a poor classification performance, for example, irrespective of the machine learning algorithm that you're going to use. So we are going to represent data points using what are called features. So features are attributes of data points that we can use. For example, if we want to represent flowers, maybe the colors of petals, the number of petals the flower has, and things like the lengths and the sizes, widths and things like that of petals could be used as features. So having good features is a central thing when you are learning things like classification models. So coming up with good features for a particular task is an art of itself, and it requires quite a lot of domain expertise. So if you want to do things like, say, image recognition, then we first need to know like what are the good features for representing an image. Things like edges or shift features are classically known as good features for representing an image. And recent advances in the field of deep learning is trying to remove this feature engineering process and try to discover useful features for a particular target task by actually using large data sets. So if you have categorical features, then you can learn things like rules. So we'll see a lot of this type of rules when we discuss decision trees. And the main challenge when you're using categorical feature is that you can't like add these categorical values. You can't add red and yellow. There's no way of distinguishing different values of a particular category. So it's very different. For example, if you have a numerical feature such as the frequency of a particular word, so then of course you can know frequency of occurrence 4 should be greater than a non-occurring particular feature. So these type of things cannot be done with categorical features. So if you have categorical data, then you can represent these as various dimensions in a multi-dimensional vector space, and a given vector can be represented as a point in this space. So you can think of a situation where each word in English are represented by dimension in this high dimensional vector space. So any document that's written in English can be represented as point in this vector space. So on the other hand, with numerical data, you can do things like addition, multiplication and things like that, and you can order your numerical data points because there's a clearly defined total ordering. And we will be using this notation r to the power n to indicate that we have a n-dimensional real valued vector space, and x is a particular vector in this space. And the main challenges of handling numerical data would, for example, be how to handle the different scales, and we might want to consider ways of normalizing these different ranges into some kind of standard range before we do any learning using those features. So there are two standard methods of doing feature scaling. So one is called 0-1 scaling, where you basically subtract the minimum value of the given data points, and then you divide that by the difference between the maximum and the minimum. The second method is called the Gaussian normalization. So you basically are trying to fit a normalized distribution, and you are trying to standardize your data. And to do that, what you do is you compute the mean and the standard deviation, and then you have this formula x minus mu divided by the standard deviation. So here is a quiz for you to try out the two data normalization methods.